Good morning, everybody, and thanks very much for the invitation and the very kind introduction. I would also love to be there. Unfortunately, I wasn't able to make it for some happy reasons. My wife and I are expecting a kid anytime now, so I wasn't able to come. But I hope you all enjoy this inspiring workshop, and I'll try to also attend as much as I can remotely. And I hope interesting things are going to come out of the workshop. So today I wanted to talk about one of the many facets of what we're missing and what we should try to build towards extending the amazing success of foundation models outside the realm of single agent learning setting, and understand how to build models that can think strategically, as well as models that could interact with each other, models that could interact with each other and also with humans. So I'm going to talk about the optimization aspect of what we would have to develop. And that has some beautiful connections to game theory and learning theory, and I'm going to come to that. So I've been thinking about this for the past 5 years, and I'm going to try to paint a picture and explain where my current thinking is. So, of course, there's amazing progress in AI, and within that progress, we have seen amazing progress also on applications that are multi-agent, like the ones that you see here on the screen. Some of these applications are explicitly multi-agent, such as the one at the top, playing difficult games or thinking about multi-robot interactions or interactions of agents such as self-driving cars with humans. At the bottom, there are applications that are not explicitly multi-agent, but perhaps they're not born multi-agent, but we're formulating them as games and trying to think about the equilibria of these resulting systems allows us to arrive at a desirable learning outcome, and two primary examples of that are generative adversarial networks and protecting classifiers against adversarial attacks. So despite all this amazing progress, and by any means do not want to discount it, there has been some amazing progress here. I want to offer some caveats. So there's going to be like 5 caveats, and that would help us introduction to motivate the talk. So the first caveat is that strategic thinking is just not going to emerge from standard training. So in the video you see here on the screen, we see a self-driving car that is trying to enter a highway, so it has the blinkers on, but that car is being antagonized by human drivers, so much so that it has to abandon the attempt and exit the highway. What happened here is that a policy was learned for the car via reinforcement learning or like imitation learning, imitating what humans do. But that's not enough to be able to think strategically, right? I mean, like changing lanes is a non-trivial task that we human drivers have mastered. We successfully use the threat strategies to change lanes, right? But we receive signals from our opponents, for the other drivers, I mean. But this is not just spontaneously, this ability is not spontaneously developed by thinking about the single agent planning problem. If you think of a self-driving car, on its own. A more recent related example is the following. So I went to ChatGPT and asked it to help me play tic-tac-toe. So I told him I'm the ex-player in this board, and and you know, like I'm about to play next. What would you recommend me to do? And here's what ChatGPT recommended me to do. Right. So there is a forced win. You know, I can play at the middle of the top row and win the game. But ChatGPT says I should play bottom in a non-winning position. I mean, you know, can everybody hear me? I yes. Sometimes hear some sound from the background, but if everything is okay, okay. So ChatGPT has seen many instances of tic-tac-toe on the internet, and I would presume that you know, perhaps by imitation learning, by seeing how humans play this very simple game, it would be able to advise me how to play, but it fails to do so. Okay? And Jeff Liang and I, Jeff Liang was a student at Harvard, and I did a lot of experiments trying to prompt engineer ChatGPT to help it play tic-tac-toe, and you know, like, unless you hold its hand a lot, it's not gonna be able to do that. That's the first caveat. The second caveat is one that is well talked about, that of adversarial attacks. So as you all have seen, I believe classifiers can be attacked by sprinkling well-orchestrated noise on the images. For example, this image here is recognized as an airliner, but this image is nothing but this image over here, which is recognized correctly as a pig, with the sprinkling of a tiny bit of this particular noise pattern. And you don't need to do noise. I mean, this is, okay, so this is a turtle that is a 3D printed, like a real object that is recognized as a rifle. But you don't even need to sprinkle, you don't need to orchestrate a lot on how you paint the picture. Even rotations can confuse classifiers. The third caveat is that if you train a model without regard to the presence of other agents in the system, this can lead to undesirable behavior. So in the example I want to give, there is a duopoly of two symmetric firms, a very standard model in economics, studying price competition. And over here, there's going to be two firms who set the price of their good in response to the history of prices they have seen in the system so far. Okay, so each of them independently looks at the past prices of the two firms and decides how to update their own price. The interesting thing that happens here is that the price that the independent learning arrives at, the numbers don't really matter, the ordering of things really matters. The price that is learned is far from the Nash equilibrium price. So there's a lot of competition here. There's two symmetric firms. There is a competitive price that they would set if they were thinking strategically about the situation. But if they run independent learning algorithms to update their prices, as it turns out, the price they learn is closer to the price that a coordinator, like a collusive player who controls both firms, would choose. Which of course is bad for the society. And I guess, like in this paper by Calvano et al., they also show how in the learn policies, deviators are punished. So this is the dance that is going to take place if, after the two policies have converged to the collusive price, one of the two players decide to do a heavy discount. This is sort of like how the other player will follow, and sort of like the two agents, right? So there's this shock here. I'm pushing, like we're pushing one agent down, and then here's how the policies respond to get back to the collusive price. The fourth caveat that I wanted to mention is that the optimization workhorse of a single agent deep learning, which is that of gradient descent or analogous procedures, is actually not successful in the multi-agent setting. So the practical experience of people working in multi-agent learning, for example, in GANs and other settings, is that the moment you have more than one agent run gradient descent in parallel against each other, the dynamics tend to be cyclic or chaotic, and it takes a lot of engineering effort to make them converge to a good solution. The fifth and final caveat that I want to mention is that in multi-agent deep learning applications, so applications where the utilities or the strategies are modeled like deep neural networks, game theory breaks, and I want to spend a bit of time discussing why. So in many of these applications, you have, like this is in the box an abstract game, right? So you have a bunch of agents. Each of them choose multi-dimensional actions. So for example, think of its xi as setting the parameters of some neural network. And its agent wants to minimize the loss or maximize the utility. In fact, I'm gonna stick with utilities in this talk, but you can think of losses if you are so inclined. So you have a bunch of agents. They all choose parameters of a neural net, let's say, and they all have a utility function that depends on not only their own parameters, but also those of their opponents. So what is different in comparison to classical game theory in these kinds of settings is that first, the strategies are very high dimensional, like million dimensional, or in this case, billion dimensional. But more importantly, the utility functions of the agents are not concave in their own choices. Okay, so these are neural networks involved. So these functions are non-concave, non-convex. They're not functions that are nice. If you like, but one thing that can work for you in these settings is that the utilities at least are Lipschitz and smooth at least almost everywhere. You can take gradients to them, and you may want to exploit that. But that's not going to save you from the fact that the moment the utilities are non-concave, you lose the guaranteed existence of Nash equilibrium and other types of equilibria. And if equilibrium analysis, if equilibria do not exist, equilibrium analysis is that doesn't apply. So what is even if you had a way to train a big foundation model using data to play to think strategically in some scenario, what is even the goal? Like, what optimization target are you gonna set out to optimize in this kind of setting if equilibria break down? So you have to develop your own notions of optimality, your own solution concepts that are valid, reasonable targets that exist in this kind of settings. So this 5 caveats are basically what motivate my talk. And I want to dwell a little more on this 5th point, just to explain, because I'm sure there's going to be question marks in your minds, especially those of you who are closer to game theory. So let me be precise about how equilibrium break how equilibrium existence breaks down, what the options might be. Okay, so let me be more precise about what I mean by Nash and so on and so forth. So a Nash equilibrium is a selection of parameters for each of my neural nets, so that no neural net I can find an alternative setting of its parameters that improves its utility, right? So all other settings of parameters are not better. Sometimes this is called pure Nash. I don't want, okay, so I'm not going to use pure Nash here for reasons that I'm going to explain in a bit. But okay, this is a Nash equilibrium. This is a very reasonable notion of optimality for neural network I. I will talk about also mixed Nashes. So mixed Nashes are maybe less well motivated in the setting of deep learning. Over here, I want a distribution over neural nets. I want a distribution over neural nets for the first player, a distribution over neural nets for the second player, and so on and so forth, so that in expectation, with respect to the product measures. So imagine that each neural net independently samples its own distribution. I want that in expectation with respect to neural nets sampled from the corresponding policies, agent I cannot improve by setting its parameters to some other alternative xi. That's going to be the notion of mixed Nash that I'm going to adopt, very consistent with what you've seen in normal form games. And finally, correlated equilibrium, which is the same as Nash, except that now I allow a joint distribution over setting all the neural nets together and thinking about single neural net deviations. Right? So it's the same equation all along, except I'm putting expectations with respect to either product measures or with respect to joint distributions. So with these notions in the background, let me try to explain what breaks down. If the utilities, this is a classical result by Debré and Rosen, if the utilities are concave, if the utility UI is concave in xi, in fact quasi-concave would work, if its UI is concave in xi and is continuous, and the domain wherein xi lies is convex and compact, then the first kind of equilibrium exists. And in particular, the second and the third, because these are more general notions. And this is enough to capture mixed Nash, mixed Nash equilibria in normal form games, right? Because in normal form games, these xi's are actually distributions over a finite set of actions. So like Nash's theorem lies at the very top of this hierarchy, right? It's not, right, so over there, it doesn't, you don't even need to do distributions over distributions because they're just distributions. But a special case of this theorem, of the existence of the first kind of equilibria I have here is actually equilibria in randomized strategies in finite normal form games. All right, so the flip side of this theorem is that if some of any of these UIs is not concave, then equilibria of the first kind may not exist. And there are easy examples that show that. Let me not dwell too much on the point, but you can create this, for example, trivial two-player zero-sum game where one player is rewarded for both agents choose scalars. So these are single parameter neural nets they're choosing, and their utilities are very simple. It's just the distance squared, or minus the distance squared. This game has no Nash equilibrium. Because basically, if x1 and x2 are different, the player 1 wants to go away. If x1 and x2 are not different, then x2 wants to go and match player 1. So there's no Nash equilibrium of the first kind. Another example of equilibrium existence failure is the Arrow-Debré model. When you have economies of scale, which means that the production costs are concave, which means that the utilities of the agents are not guaranteed to be concave, right? Because utilities are minus costs. Now, if the costs are all concave, minus the costs are convex, so utilities have convexities in them, perhaps. And of course, generative adversarial networks is an example of that, because you have two neural nets, the generator and the discriminator, trying to set their parameters in a way that neither of them can improve. A correction to this non-existence comes if you consider mixed Nash equilibria, right? So if the domains wherein people choose strategies are convex and compact, then and the UIs are continuous, that suffices to guarantee the existence of mixed Nash equilibria. Except the support is going to be infinite in general, and uncountably infinite in general. So that wouldn't be a nice equilibrium notion for understanding deep multi-agent settings. Right, so by considering mixed equilibria, you can resurrect existence, except you have to use infinite supports. And perhaps that's not well motivated. Finally, if the XIs, the domains, are not compact, even mixed and correlate equilibria may not exist. And a nice example of this situation is a two-player game that is called Guess the Larger Number. Both players choose a real number, and whoever chooses a bigger number than the other gets 1 point, the other person loses 1 point. So this is a two-player zero-sum game, but it doesn't have mixed or correlated equilibria. Because basically, whatever the other person does, the other player can move their support to larger numbers and beat the other player. So this is kind of like my short intro into the caveats, which motivates the focus of this talk. So I want to tell you a little bit about how I'm thinking about dealing with these issues. Right, so the questions I want to ask are these. First, what are meaningful and practically attainable optimization targets in the setting? Why is it that gradient descent struggles, even in two-player zero-sum cases, for example, in GANs? And is there a way to develop a generic framework for multi-agent learning? And here I'm going to say that, part of the big success, like a big reason for the big success we have seen in single-agent settings is the fact that we have lots of optimization frameworks and hardware where we can try all sorts of different ideas. So to make progress in the multi-agent front, it would be great to have a generic framework that people can just use to train agents in multi-agent situations. Instead, what is happening here is that the algorithms are so specialized, depending on the underlying model, that you need a lot of domain expertise to even start making progress, and also you need specialized algorithms to train your agents. So it's not open enough for a whole world to work on it. So what I want to ask is there a way to develop such a framework that would unleash the creative power of people to work on these kind of things? What I'm going to ponder in a little bit is whether, in terms of solution targets that are guaranteed to exist and are attainable, if there is a generalization of the notion of local optimum, which is the target, the optimization target in single-agent learning, I want to ponder whether there is an analog of that actually is guaranteed to exist and is also computationally attainable in the multi-agent setting. Regarding the second question, I want to ask, is this is there some underlying intractability which explains why gradient descent suffers, or is it the wrong method for the problem being solved? And finally, and that's again coming back to this earlier, perhaps a bit philosophical point, do we need to study each and every different situation separately? Or is there a way to open it up and like have a generic way to approach these kinds of problems? Of course, like by this I don't mean that like if there is structure that you shouldn't throw it out of the window. But if you're a bit agnostic about the structure that may exist in a multi-agent setting, can you just like choose some architecture for a neural net and for every agent, and have them all trained together in a way that like something nice happens? So these are the questions that I want to ask, and let me get to the meat of the talk. So again, this is the setting that I'm talking about, and here I'm going to assume that the UIs are ellipsoids and smooth almost everywhere. In fact, I will assume that I have gradients everywhere to simplify the discussion. You can extend most of the stuff I'm talking about to situations where the gradients are almost everywhere existing, by taking but like it's gonna make it tougher to the notation. So I'm just gonna stick to existence of gradients everywhere. And the other thing I'm going to throw in the picture, perhaps is relevant, is that sometimes in a multi-agent situation, one agent imposes constraints on the other agent. So perhaps this guy is producing something, this guy is buying something. So demand cannot exceed supply. So there are some constraints that tie together the actions of all the agents here. Other than that, my UIs are going to be continuous, but I'm not going to assume and smooth, but I'm not going to assume concavity of the utilities. And I want to address the first question I was posing earlier. What are meaningful and practically attainable optimization targets in this setting? That's the question. That's the main question for this talk, for the remainder of this. So by meaningful, I mean, okay, so that it's not well defined, but I definitely want it to be universal. I definitely want whatever solution concept I propose to be guaranteed to exist. So I'm not asking my training algorithm to find something that may or may not exist. Also, it's important that whatever my solution is verifiable with the information that agents have about their utilities. Right. So, for example, things like find me a point that is close to a true Nash equilibrium or whatever is not the right kind of solution, because whatever I demand should be verifiable by access to the gradients of the utilities. That basically is the information that people have. So, practically attainable, I want some first-order method like gradient descent to be able to get there. And of course, the obvious thing to do, like I'm gonna do several attempts with that idea. The first attempt is kind of going to work, but not quite. And then the second idea will work. So the obvious idea to define a nice solution concept for this setting is to take the solution concept of choice in single agent learning and try to generalize it to this setting. So what is the solution of choice in single agent deep learning? Targeting local optima of the loss function or the utility function of the agent. Similarly here, I can try to target the obvious generalization of that, which is what's called local Nash equilibrium. What is a local Nash equilibrium? Well, it's a collection of choices for the agents, so that for every player I, what they're playing, the parameters they're using right now, is a local max of their utility, fixing the other guys, and trying to locally improve the utility by looking at the ball around xi star. Okay, so That's the analog of a local optimum. If n equals 1, this is the standard notion that is used in deep learning, single-agent deep learning. So this is the natural generalization of that. And of course, one has to be precise about what they mean by local max, and there are many ways to define local max. I mean, there is the, I guess, mathematical way to define local max, and then there is the optimization way to describe local max. So here's the babyest version of what local max may mean. It's what's called first-order local maxes, right? So, which is that it's max with respect to the first-order Taylor approximation of the utility around that point, right? So it's a notion that can be verified by looking at the gradient of the utility at xi star. Of course, you can define a hierarchy of this, right? You can look at second-order local max by asking that the gradient is 0 and the Hessian is negative definite locally, or a third order, and so on and so forth. Okay, so for now, I'm gonna stick to first-order local max, which basically means max with respect to the first-order Taylor expansion, which basically means I want the gradient to be 0. In fact, let me be precise. What does it mean for xi star to be best response to the other guys as far as the first order the Taylor approximation of the utility can tell? It means that agent I must find themselves in one of two scenarios. This orange set here is the constraints imposed on deep net I by whatever the other deep nets are playing. So this is like, this notation here means that, like this script S is the constraint set of all players. Script set as I is for player I, and it depends on what the other guys are doing. So this is the set. This is given what the other guys are doing. These are all the options that player I has. And for them to be satisfied, as far as the first order Taylor approximation is concerned, they must be either playing something on the boundary of the set, where the gradient is perpendicular. So if they were to do a gradient step, they would step outside, and if they were to project back, they would land where they started. Either this is the case, or xi star is inside the domain, but the gradient is 0. In both cases, first order information doesn't help me improve my utility. And a compact way to write this is to say that if I start at xi star and I do a gradient step, and then I project on the constraints imposed on me by the others, I get back the point that I started. Which basically my solution concept, like in a circuitous way, arrived at basically saying it's a fixed point of gradient descent, right? Because this is literally expressing what it would mean to be at a fixed point of gradient descent. So this is my first try at a generalization of local optima from single agent learning to multi-agent learning. Oh, I see, okay. What time is it? Yeah, okay, yeah. Cool. So a few results about this. So the good news are that if S, the set that the constraint set, is convex and compact, a first order local Nash equilibrium exists. So that's good news. So the generalization of local minima, local optima to local Nash equilibria was successful on that front. And also, it's verifiable with the gradient information that agents may have about their utilities. They don't need to do very hard computation to verify that they are at the local Nash. The trouble is that if I wanted to extend this to second order local Nashes, they're not guaranteed to exist. So that's a bummer. So this is really my only option. If I were to extend to second order local Nashes, it wouldn't work. And you have seen already an example like this x1 minus x2 squared game was degree 2. So if I do second order Taylor there, nothing changes. And that didn't have a Nash equilibrium. So over there, second order local Nashes and Nashes, global Nashes are the same thing. and it doesn't have global Nancy. So, first order is really the only option that I have here. So that's a piece of bad news, but the biggest piece of bad news, okay, even if we stick to the first order local Nash equilibrium, it is intractable, right? So what I showed with Constantinos Daskalakis and Daskalakis a few years ago is that you need exponentially many queries to the utilities and their gradients to arrive at even an approximate first order local Nash equilibrium. Right. So like not only is the solution concept quite compromised in the sense that we're only looking at gradients, but computationally speaking, it is intractable. It does exist. Okay, so we corrected that issue, but it is intractable. It is intractable in this sense. Any first order method will have to make exponentially many queries to arrive at it. But also in a stronger sense, that even if you have white box, even if you can look at the details of the function, the problem is pretty hard. So this is where we are right now. So the obvious generalization of local optimum doesn't work. So we are far from getting, at this point, far from coming up with a framework for multi-agent deep learning that is generally applicable, because even though we have a notion of a solution concept that exists, it is hard to identify with first order local methods. So let me tell you a little bit how in recent years, like after 2021, I've been trying to rectify the situation, and there are some successes. Let me talk about them for a bit, and then I'm going to open it up for questions. So the first idea is to say, yeah, okay, Kostas, yeah, the problem is intractable, but this is just a worst case result, perhaps in an average sense, like most of the games that we encounter out there are tractable. So why don't you go and develop an algorithm that like it's guaranteed to converge to a local Nash equilibrium, even though sometimes it takes exponential time. Perhaps in practice it works. So we went out there and exploited the connections revealed between this problem and PPAD and fixed points to develop a second order dynamics that is guaranteed to converge to a local Nash equilibrium. So this dynamic is not gradient descent. Gradient descent is known to cycle. But we developed a method that, right, so this is an example of what's happening. So over here, you see the trajectories of gradient descent, like starting from somewhere and kind of like getting in a cycle, right, no matter where you start inside, right, so here is the Nash. The Nash is at the center. If you start there, gradient descent stays there. But if you start anywhere else, either inside of the cycle or outside of the cycle is going to cycle. So this is our method over here. It just goes straight into the local Nash. But it may take exponential time because, we cannot avoid the worst case result that we have. It's also a second order method. So an interesting open direction is to turn it into a first order method that by cutting corners, that practically converges fast. That's one attempt, sticking with the notion of local Nash equilibrium. Here's another attempt that I'm excited about these days, is to consider randomizations. So allow me to randomize over neural nets and consider notions of local correlated equilibria. So what's a reasonable way to define a local correlated equilibrium in non-concave games? Roughly speaking, so I'm going to talk about coarse-correlated equilibrium. In ongoing work, we think about correlated, but it gets more messy. So let me talk about coarse-correlated equilibria. And I want them to be guaranteed to exist, the way I define them. So here's the notion that I'm proposing. And I'm not being very formal, because if I was formal, I would have to do projections and stuff like that. So let me not be formal and convey the intuition. So I want a distribution over ways to set the parameters of my neural nets. This is a vector of strategies for my neural nets. So I want a joint distribution over how to set my neural nets so that every neural net has an expected zero gradient. So there's no, under my distribution P, there's no consistent direction that any neural net can use to locally improve their utility. If the support of this thing is 1, this is exactly local Nash. Because like local Nash was set the parameters of the neural nets so that nobody can locally improve. So everybody is facing a zero gradient locally, okay, with projections, but I'm skipping that right now. But what I want to ask is, okay, like, if I increase the support to bigger than 1, is there a polynomially large support, not exponentially large support, but polynomially large support, so this thing becomes actually tractable? This is what I'm asking. And the answer to that is actually yes. So if the domain, the constraint set is convex and compact, and the UIs are Lipschitz and smooth, there is actually a support of polynomial size for my distribution P over how to set the parameters, so that this local CC exists and can be computationally efficient, computed efficiently with gradient descent. And I think with that, analog is generalization to correlate equilibria. I started seeing glimpses of a general framework that could work in this multi-agent deep learning setting. So I have 5 minutes to go, and I wanted to wrap it up here. We thank you for coming to my talk and inviting me and your attention.
Great. We just unmuted the room here. Thank you, Kostas. Oh yeah, we all applauded. Why we applauded?
Thank you.
Okay, great. So we do have some time for questions. Yeah, Hoda.
I have a question about whether there is an intuition as to why, when we have multiple agents doing gradient descent, it would tend to either cycle or be chaotic, and how. First of all, how often does it happen, and what's the intuition as to why it happens, and which one happens when? Not sure if you heard the question.
Yeah, that's a great question. I should have given some more intuition about that if I had time. So basically, like, one has to think about a good intuition can come from thinking about two-player zero-sum games. Compared to single-agent settings, right? So, like, why does gradient descent converge in single-agent setting? Well, because, you start somewhere, you query the gradient, you follow the gradient, your utility improves, and you keep going, and because the utility improves, the utility itself acts as a potential function, saying, look, that, like, if I'm in a compact set, the utility must have a maximum. And because every step of gradient descent, I'm making progress, I'm increasing my utility, the utility itself is a potential that has to hit a wall, because there is a maximum of my function over a compact set. So this is why it converges in single agent settings. Now, turning this on its head, if I have a two-player zero-sum game, and people take steps, whatever one improves, the other one, right? Like one player is trying to increase the utility, the other, is trying to decrease it, and they can get into cycles very easily, right? Like, think about the x1 minus x2 squared game that I was talking about before. But perhaps that's even a bad game because it doesn't have equilibria, right? Sorry. The main issue is that there are no equilibria, right? But think about local equilibria, which are guaranteed to exist. The issue that gradient descent has issues is because of this thing, that whatever progress one guy is making, the other guy is destroying. There's no potential function that improves. And this is intimately related to the fact that the problem is PPD complete and related to fixed points. So fixed point problems, right? So fixed point problems are known, at least, like, with our current understanding of the complexity theory of total problems, fixed point problems and all problems in PPAD are not known to have a potential function. Like they cannot be solved by following a Lyapunov function. So this is perhaps the deeper reason why. So I gave some intuition. The progress one way makes, the other one destroys. And also the deeper reason from a computational complexity standpoint is that PPAD is not in PLS as far as we know, so it cannot be solved via the Lyapunov type arguments.
Mike?
Yeah, Michael Wellman, very interesting ideas. Deep learning works not just because you can reliably or provably find local optima, but because somehow practically the local optima you find are not terrible, are often really good, or maybe close to global. Are there any intuitions or reasons to think that that property would generalize over to the multi-agent setting?
Yeah, so that's a great question. So today I talked only about the optimization aspect, like the fact that I want to have an algorithm with guaranteed convergence somewhere. In single agent settings, you don't want the global opt, you want the local opt for the reasons that have to do with generalization. So you want to select something that doesn't overfit the training data. And I definitely think that in multi-agent settings, these same phenomena are going to arise. Today's talk had nothing to do with generalization, but it's a very important thing to think about once we bring data into the picture. When we think, for example, about concrete applications, like say multi-agent reinforcement, we have natural distributions, and we are talking about generalization. But I guess I was talking here at a very abstract setting, so I did not address generalization at all. I should also say that despite the fact that people have intuitions about what gradient descent is trying to do in single agent settings, as far as I know, there is no even mature theory there. I mean, there are some results about what local optima gradient descent selects, but still the theory over there is still not mature enough. So the same phenomena are right, but it'll take a lot of work, not just in multi-agent, but also single agent settings to figure these things out. Yeah.
Yeah. Thank you for your insightful talk. And I have a question for the correlated equilibrium part, which you covered rather quickly. So, given the definition, are we seeking the probability measure over the strategy space? Is that what you mean by learning the correlated equilibrium? Because I wonder, how can we do this with gradient descent?
So what happens is very similar to what happens when you do non-regret learning in normal form games, which you might be familiar with.
Okay, so empirical play. Okay, empirical frequency of the play. Is that what you mean? Okay.
Yes. So you want that the empirical frequency of play has this property that over a period of interacting with the other agents, if I look at the empirical distribution of play, every agent thinks, okay, there's no consistent way I could have improved my parameters.
I see. Then if that is the case, then probably the solution concept should be the empirical play, the discrepancy between the empirical play and the true correlated equilibrium, should be less than epsilon. Because when I look at the definition you're proposing here, we're not seeing the empirical frequency per se. So I was wondering, what are we proposing here by looking at this gradient criteria?
Yeah. So I guess there are two questions here. What is the solution concepts and how you arrive to it, right? So
that's true.
There are right. So one way, the way gradient descent will compute this, is by running for a bunch of steps and then averaging in the right way the steps that it made. But the definition itself stands on its own right? It is a distribution, in the standard sense that there is correlated equilibrium in game theory, and one way to arrive at it is to run no-regret learning, right? So over here, basically, what is this gradient about, right? This gradient says that in expectation, there's another way to write this, right? Which is that if I look at the expectation. And I think about my utility, my utility under the distribution, which is, if I play X star versus, I cannot write on this thing, versus what would have happened if I consistently deviated in some way. So if I, for example, if I mixed what I was recommended to play, right, with some other action of my choice, if I mixed in delta to what I was recommended, delta some other action x, that would not have improved my. This is where gradient. Again, I have to do projections and stuff, but this is what I'm trying to say here. That like gradient is the best direction that you could try to deviate to in an average sense, right? So you want that no player has a consistent direction where they could consistent direction x here. Sorry for the mess, but that they could have improved.
Thank you.
Yeah, it's like if the game was concave, this would be exactly CC. If the game is concave, this is exactly CC. If the support of the distribution is 1, then this is exactly local Nash. So this is the natural generalization of both concepts, like the local Nash for non-concave games and CCEs for concave games. This is the same notion. Yeah.
Thank you.
Thank you for your amazing talk. I just want to ask, what are your intuitions that multi-agent may help training large language models?
So sorry, can you repeat? What about large language models?
Yeah, your intuition that multi-agent can help.
Large language models?
Yes.
Yes, so I think large language models are not, if they learn strategy, it is via imitation learning, right? By observing what, people perhaps are doing in the corpus of data that they observe. So if you can stance that, whenever you see strategic behavior in the corpus of data, some player is maximizing something, then my proposal would be to think about, the fact that there is a pre-selection that has taken place, which is strategic, right? So the problem with imitation learning is that you're observing an expert, who has already optimized over a set of alternatives. You only see what they chose to do. You don't think about the counterfactuals. That's not part of your training. I mean, you try to literally are trying to imitate. So if you want LLMs to be more strategic, you have to, first of all, identify a corpus of data that contains strategic behavior, and then change the way you train the LLM to take into account that, the agents that it's observing there are optimizing something, and they're, right? Imitation is not enough, basically. In the work that I mentioned earlier with Jeff and Liang, we thought about that a lot. So we thought about various ways to either do prompt engineering for the LLM, or to, do fine-tuning of the LLM, or to take the embedding of the LLM and plug it into a neural net that can do, like Monte Carlo tree search or whatever. We thought about all these alternatives. But the point is that if you just train a plain LLM to imitate what it sees, it's just not going to be strategic.
Okay, great. Denny?
I'm curious to understand how many of these results do not hold once you start assuming Lipschitz continuity on higher order derivatives. It feels like if you had second order derivatives be Lipschitz continuous, the impossibility results for local Nash wouldn't hold. And in some multi-agent settings, you really need to know about the higher order derivatives, upper bounds, in order to be able to understand better the upper bounds on the computational tractability of them.
Yeah, I guess to this question, that's a great question. So to this, I mean, in this result here, right, on the second order method that I mentioned, we are going to be exploiting second order smoothness. But basically, one thing you have to realize is this x1 minus x2 squared game is a killer, right? I mean, this is a game over a compact set, so plus minus 1. It's super, as smooth as you want, right? Because, it doesn't have two derivatives, and it's the compact set, so they're both bounded. But local Nash, like Nash, global Nash don't exist. Second order local Nash don't exist. The only option is first order local Nash. So it is a problem. This yes. Yes, I didn't hear if there was a follow-up. Yeah, that was my thought on this question. Yeah.
Okay, great. Maybe one more question. Yeah.
Given the difficulty of designing gradient-based methods for multi-agent learning, what do you think about the PSRO style family of methods where you alternate between solving a finite normal form game and solving single agent optimization problems?
Yeah, that's a great question, and it's as if this question was planted because I had one slide. There was one slide that I had to skip because of lack of time. So, yeah, I don't know, is it okay to just go through this one slide to answer this question? So,
yeah, a couple minutes, or, yeah, sure,
okay.
Please do.
Yeah, I guess, so this slide is about exactly this, the PSRO. So, like this is kind of like taking a different stance, right? So here we're thinking about the local correlated equilibria. In this alternative perspective, you say, like, forget about it. Let's think about global correlated equilibria. Okay, so problem one is they may not exist, right? They do exist under compactness. If your constraint set, if your strategy sets are compact, they do exist, okay? But as I was saying earlier, in this game, guess the larger number, they don't exist. So what you want to understand is under what conditions, A, they are guaranteed to exist, even without compactness, and B, there are simple procedures that converge to them, like PSRO. So you want to understand, for example, conditions under PSRO and double oracle algorithm converge to global equilibria. And here there is some progress so on this front by us and others. So on the first question, on the global correlated equilibrium existence question, basically you can show that if your utility matrix or tensor not contain a scaled copy, guess the larger number game, then a global correlated equilibrium is guaranteed to exist and to be finitely supported. So that's the cool result number one. Formally, the lack of existence of the scaled version of guess the larger number game means that the Littleson dimension or the sequential or the Mark complexity of the game is finite. But let's ignore that comment. And to your question, what we established in this recent paper is that a variant of the double oracle algorithm is both guaranteed to converge under this condition that there is no copy of the guess the larger number game, and it also has efficient computational complexity. So yeah. So it's not like like the number of steps it will take has to do with the support of the correlated equilibrium. But that, which is finite, but could be large. But what's important here is that every step you can compute efficiently. So like in PSRO, every step you want to be able to compute every step of PSRO efficiently, in the hopes that eventually it will settle at the global correlated equilibrium. So we have progress on that front. So we have a variant of the PSRO algorithm that is guaranteed to exist and has efficient per step computational complexity, and that ties in very nicely with notions of online learnability, like Littleson mentioned, and sequential random mark complexity. For those in the audience that don't know PSRO, or the double oracle algorithm is a very natural algorithm which says, let me just define a meta game. Let me just choose, I have a very difficult game. Let me just, for starters, choose 5 mixed strategies for one player and 5 mixed strategies for the other player. 5 is not important, but some finite number of mixed strategies for one player, some finite number of mixed strategies for the other player. Now let's try to solve this meta game. So now I have a distribution over my 5 mixed strategies and a distribution over the opponent's 5 mixed strategies, so that we have an equilibrium of this finite game. And then what it says is it asks each player to say, given the mixed strategy of the opponent, can you bring in a new mixed strategy that improves your utility? And you add it to the set of, you had 5 before, you added a 6th one. And you do the same for the opponent. And you keep going in the hopes that at some point, you will arrive at a finite meta game such that no player can innovate, no player can introduce a new mixed strategy that can substantially improve their current utility. This is what is the double oracle algorithm, and its instantiation to multi-agent reinforcement learning is called PSRO, but this is a simple idea. So we have a variant of that is guaranteed to converge, and it's sufficient. Yeah, so thanks for the question. Sorry for taking this detour.
Oh, that's perfect.
Yeah.
Thank you. That was fantastic. Thank you, Kostas. Well, thank you again.
Thank you very much.